Okay, all good. You ready to start, Siyi?
Yes.
Super.
Yeah.
In which case, let's welcome you to this month's Rocky World discussions. We're very excited to be here on what in England is a very cold and wet day. And Siyi today is going to be talking to us about planetary systems around white dwarfs. Siyi is currently at Gemini Observatory, and I think she'll introduce a bit about herself and science in the talk. And the talk should be for about 30 to 40 minutes. And Siyi's asked that if you have any questions during the talk, that you just raise your hand or put something in the chat. We can try and answer them during the talk as well as in the discussion after the talk. And just for some kind of Zoom netiquette, please use your full name and keep muted throughout the talk, but use your video when you want to speak to ask a question. So with no further ado, I shall hand over to you.
Oh, thank you. Yeah. Let me share my screen. Okay, Amy, can you give me a thumb up if you can see this? Okay, awesome. Thank you. Yeah. Hi, good morning, good afternoon, good evening, everybody. My name is Siyi. I am an astronomer at Gemini Observatory and NOIRLab. Very happy to, today I'm actually in Boston, so I'm on sabbatical right now. So I'm currently at MIT, and it's actually a very sunny day. So yeah, so very glad to be here and to tell you a little bit about what I have been working on, which is actually about planetary systems around white dwarfs. Yeah, so before really getting started, I feel like I have to tell you a little bit about Gemini Observatory. That's where I work. So we're named after the constellation Gemini. And why is that? It's because we actually have two kind of twin telescopes. One at north and in Hawaii, that's where I'm based, and one at south in Chile. For a non-observer, you might ask, why do you need two telescopes, right? So you need two telescopes so you can look at different parts of the world. One look at the northern hemisphere, different part of the sky. One at northern hemisphere, one at the southern hemisphere. And also we are about like 6-7 hours apart. So more likely one of us is in dark time if you want to follow up any kind of exciting things that just happened. And then for me, yeah, I live on this island, which there's a lot of active lava going on. So this is just actually happening in June. I think it stopped, and then it's the fourth time Kilauea has erupted again. So this is an island with a very active volcano. So for me, it's really inspiring to think about the island I'm living on, and then trying to figure out what's happening in these rocky worlds out there. Are there things like this also happening? Right. With that, let's talk about the research, the science part. Yeah, so this is the solar system. We know that today it's kind of busy. There's the sun, like the star in the middle, there's terrestrial planets, there's gas giant and ice giant, gas giant. Solar system also kind of have two debris belt, which is the asteroid belt and also the Kuiper belt. So one research question kind of really drives me is what happens to the solar system in about 5 billion years? Like, will we still be here? And what happened to the planets? What happened to the asteroids? So to me, this is kind of my cartoon thinking about solar system in 5 billion years. And the sun will no longer be like a main sequence star. It will become a white dwarf. And then during the process, it will clear out a lot of the things kind of in the inner edge. So maybe roughly 1 AU. So Earth is kind of on the edge. Earth might or might not survive the process. And then, but the outer planet probably will still be there, but then will orbit a little bit further away from the central star. And then because of all these rearrangements, occasionally those minor objects, I use planetesimals, but it could be like asteroid, comet, or things, would actually experience some perturbation to go into the tidal radius of the white dwarf and then become tidally disrupted. And this process will create a lot of dust and gas. And then it might take a while for this asteroid to completely go away. And we actually have observed like all these things. Sounds like a fairy tale, but we actually have observed disintegrating bodies. We've seen dust and gas. We've also seen planets around white dwarfs. So everything really seems to be coming together in like kind of what's happening here. Then just a little bit more background about, since I talk about white dwarf. So what is a white dwarf? The white dwarf is the end stage of stellar evolution. So more than 99% of the stars, like in the Milky Way, will end their life as a white dwarf. Just like the sun will end their life as a white dwarf. So this is kind of the life cycle of the sun. That's where the sun is right now. I said, oh, in 5 billion years, so the sun will actually become a white dwarf. And so this is one of the famous white dwarf. Actually also, yeah, the closest white dwarf. So it's a Sirius B. So Sirius is a bright star at night. You can see with your eye. And so this is a white dwarf. So that just give you an idea. So this is a binary star system. White dwarf is very common, but they are pretty faint because they are very small, right? So relatively speaking, they're pretty faint. So they can be a little bit hard to find. Then just going through a bit more, most of the white dwarf, so all white dwarfs, so no more nuclear reaction going on. And then most of the white dwarf actually have a carbon and oxygen rich core. But then when you look at it, you mostly see its surface. So it's either had a hydrogen dominated surface or a helium dominated surface. Because white dwarf are very, very dense. So like the atmosphere is actually pretty clean because kind of the heavier elements would settle out of the atmosphere in a very short amount of time. So this property will come in handy in a very little bit. Yeah. All right. So these are my like 3 introduction slides. Maybe I'll ask. Maybe I'll make a pause to see if there are any questions on kind of an introduction before, or any question about white dwarf before I move on to actually talk about what I want to talk about. Okay, I don't see any. I guess we're all on the same page. Okay, so this is kind of an outline. I'm going to tell you how. So I'm an observer. So I will tell you how I'm trying to observing the solar system in 5 billion years. And then specifically, I kind of want to focus on 2 topics. First, hopefully I can convince you that these kind of white dwarf planetary systems are really good to understand the composition of those extrasolar planets. Yeah, let's get started. We probably don't need this for this audience, but still, I just want to show a little bit about, so now we have detected about more than 5,000 exoplanets, right? So the next question is really trying to better characterize them, like what are they made of? What are their chemical compositions and what are their mineralogy? But from directly detecting exoplanet, it's kind of hard to do. So this is from kind of mass radius relationship. This is work done almost 20 years ago. But anyway, these days it's a similar idea. Kind of, you can make this kind of mass and radius diagram. So this is mass, this is radius. There are some solar system objects there, and then you can do calculations, say, based on different planet composition, what kind of mass radius relationship do you expect? Now we have a lot more data. We can do the measurement much, much better. But to me, intrinsically, it's still a hard problem, right? Because you measure mass really, really well, you measure radius really, really well. But there are so many free parameters to get the composition. So it's really like, it's kind of difficult to tackle the problem from this angle. But we can do it with white dwarfs because in a way, it already break up the planetesimals for you. So here's the idea. So basically, we are seeing kind of a lot of asteroids, like they have been disintegrated around the white dwarf, kind of within the tidal radius, right? And then the material will be falling onto the white dwarf. They get accreted onto the atmosphere and then kind of falling onto the white dwarf. And then the nice property about the white dwarf is the atmosphere is actually very clean. It's basically either hydrogen or helium. And compared to a normal main sequence star like our sun, the sun has a lot of metallicity. Astronomers call metallicity. It's really anything heavier than helium. So it's like kind of metallicity. So the sun intrinsically has a lot of metallicity, but for white dwarf, it doesn't really have any. So it's kind of what you see is basically what's coming out of there. So that property makes it really easier to do this kind of analysis. Yeah, and if we use kind of the best spectrograph to really look hard at them, we find that this kind of, we call polluted white dwarf, basically means we don't really expect the material to be there. We find that they're actually pretty common. Between 25 to 50% of the white dwarfs are actually polluted. So, and most of these pollution we think come from accretion of these extrasolar planetesimals. So yeah, this is a very common phenomenon. So here I'm kind of showing a number of like the backline is the number of white dwarfs observed, and then the black line is the one that must have been accreting, and the gray are the ones that we are a little bit unsure, like maybe there's something else going on. That's why we said it's a big range, but it's between 25 to 50%. And exactly how we do it is by using high resolution spectroscopy. So this is focused on one kind of the strongest optical lines. And so this is calcium K, which is also a very strong line in the solar spectrum. So you see, so here we are showing the log number ratio between calcium and helium. So you see, like in this object, we think it's an upper limit. And then in the other object, we have a detection. Just want to say in comparison, the solar value is minus 5.7. So we are sensitive to a very, very small amount of material, like almost like 5 orders of magnitude, like fainter, 5 orders of magnitude smaller than under the solar value. We are still sensitive to that. I know many of us also very interested in like the volatile elements, and for those we really need a UV, because a lot of the volatile life like nitrogen, sulfur, carbon, they are really in the UV. So you need an instrument like COS on the Hubble Space Telescope. So you really need a very good instrument and big telescopes in order to do this kind of work. And then to give you a sense about how many polluted white dwarfs are really out there, right? We find that maybe one element detected. In most cases, they're probably calcium because that's the easiest detected. There are about 1,000 such systems. And then if you want to do something, you need at least 2 elements, right? So there are about 300 polluted white dwarfs in this. And then if you need more than 4 elements, which you can really kind of back out how it is, there are about 30 elements. So I think a well-characterized sample is still really small, and we are working on really to build a larger sample to have a statistical sense about what is the properties of those extrasolar asteroids that's falling onto the white dwarfs. Yeah, so here's the kind of we're moving from the astronomer's periodic table into this periodic table. So all the highlighted elements here are the elements have been detected in polluted white dwarfs. So I thought that's quite good. There's about 24 different heavy elements have been detected. And then just the lithium, beryllium, potassium, it really only happened like a few years ago. But then again, like I think ideally we want all polluted white, or we want to have a sample of polluted white dwarfs with all these elements detected, right? But I think in reality, like basically we don't have one polluted white dwarf have all these elements, so just different systematics or like different things. So it's something like as an observer we are working on. Okay, so what do they really look like? So for the sample, about 30 also very well characterized polluted white dwarfs. We find that they seem to be pretty similar to the rocky object on Earth. They are all really dominated by oxygen, iron, silicon, and magnesium. So here we are showing the mass fractions. So on the right-hand side is the composition we see and on different polluted white dwarfs. And here I'm showing Earth and the comet Halley for comparison. Yeah, so you can see, I guess, to zeroth order, we didn't find anything super exotic. It's always oxygen, iron, silicon, and magnesium. And then occasionally you do see some carbon. For example, like comet Halley has a significant fraction of carbon, right? So we do have 2 systems which also have quite a lot of carbon. But most cases, the carbon abundance is actually pretty low. And then if you look at some object here, they really have a lot of oxygen. They have so much oxygen that there are not enough other elements to combine with the oxygen to make like MgO, SiO, FeO, or Fe2O3. So in that case, we think these objects might also have a lot of water, like in terms of H2O. And then on the other end of the spectrum, you see we also have a few objects that seem to be iron rich, that have like a lot of iron. So we think they are good analogs to Mercury's that is iron rich. Yeah, and if we zoom in a little bit more on the volatiles that we talked about. So here I am plotting the number ratios of carbon over calcium and the sulfur over calcium. And then a little bit busy, but anyway, so the polluted white dwarfs are the blue bars. And then the chondrites are here, other meteorites are here, and a local FG stars are here. So this, I think this really shows the volatiles is very heavily depleted in like the polluted white dwarf. So there's only one star, which is the same carbon-rich object we showed earlier that basically have the abundance similar to the kind of stellar value. everything else is like depleted in both carbon and sulfur. We also kind of see the same thing in the chondrites, right? And the meteorites in the solar system. Basically, like the volatile, somehow like the volatile material is not incorporated into these material during the formation. Yeah. And then if we take even one step further, this is actually work done by Amy. If you try to look at a sample of system and trying to ask, so here they are trying to assess the process of differentiation. Basically, the question is how widely spread is differentiation? So here they are focusing on the calcium to iron ratio, and this is like the distribution that we have observed in like over 100 polluted white dwarfs. So you see like the distribution in polluted white dwarfs look like this, which is the magenta line. And while if you take a sample of nearby stars, it look at this, which is the solid black line. And they don't really agree. Like, so basically, if you take the distribution from the stars, if you're just starting from the star composition, you can't really make this distribution of polluted white dwarfs. And after going through some calculations, they figure out the best match actually is this red line. So you need a differentiation, and you also need additional heating. So just from this work, just arguing as an ensemble of these materials falling onto the white dwarfs, we think a kind of extrasolar rocky materials probably are, a lot of them seem to be differentiated. Basically, you need a differentiation to happen in order to explain this trend. And then here's another fun exercise we've done is we tried to take one step away from the elemental composition and say, let's try mineralogy. Can we use the measured element abundance to classify the possible mineralogy of an extrasolar rocky planet? So we first started with a classical ternary diagram that's used in the solar system. So you can see like the sun, like Earth, and all the materials kind of very nicely fall along this line. And the diamond and the abundances we've seen in polluted white dwarfs. So we see quite a lot of them actually fall into this classical ternary diagram, which is good. But we do have some objects like fall out of this ternary diagram. So we kind of have to come up with additional ternary diagram to kind of fit those material in. So just based on that, we seem to be saying like, oh, there are some like exotic mineralogies that we have not quite seen on Earth, but we are finding in those polluted white dwarfs. Okay, with that, give me the first part of my summary. Hopefully I convinced you that we can use polluted white dwarfs to probe the chemical compositions of those extrasolar planetesimals. I think there's quite a lot of work to do. But I guess to general order, like we find oxygen, magnesium, silicon, and iron are in familiar proportions. Now we are trying to get a bigger sample with more elements detected. And we are also trying to work on these minor and trace elements and trying to see what they can tell us about the composition. So maybe I'll make pause here to see if anybody have any questions on the polluted white dwarf part. I guess people are happy about this as a method. Claire?
Hi, can you hear me?
Yeah.
Okay, yeah, really great so far. I just wanted to ask if these bodies are differentiated, why don't we see the complement of the other part, or do we? Like, if we're seeing different accretion events from different bodies, shouldn't they add up to be the bulk composition?
Yes. Okay. Yes, I think that's a really good question. So thank you. Yeah. So I just first let me make sure I understand. So I think your question is if it's a differentiated object and if an entire body got engulfed by the white dwarf, we should still see the bulk composition, right? For example, if white dwarf swallowed an Earth, it probably would still get out a pretty chondritic composition, right? Yes. So yes. So first, I agree. Yes. So if it's a differentiated object and if the entire object got swallowed by a white dwarf, yes, I think we will see the chondritic composition. But I think in this case, I think it actually means the body is differentiated and there'll need to be collisioning happening too. So the collision may be like we haven't seen cross material, but maybe like the core, somehow the core material get accreted to the white dwarf first. Or like maybe like the mantle is already happened and then we are seeing like the core basically accreting onto the white dwarf. So basically, we are kind of seeing fragments of a differentiated object. We're not seeing kind of an entire differentiated object. Does that kind of make sense? Okay, thank you. Yeah. Yeah, so in a way, I feel like this almost says it's a lower limit, right? So there could even be more objects that are differentiated just because it's a whole material that coming in. So we can't really tell apart from an undifferentiated body.
So you've got another question in the chat.
Yeah, okay, let's see. May I ask why these remnants of rocky planets can exist when in the final stages of red giant? And this all debris should have been all blown away by the star wave. Yes. So okay, and I think that's a good question. So it's asking why the remnants of these rocky planets can exist. So maybe I'll first start with I think our current understanding, right, is during the red giant stage and the stuff, not all the planets would be gone. And it's like, say, in the solar system, probably everything within 1 AU would be engulfed and destroyed. But then everything beyond the 1 AU, they can actually survive the process. Like Mars probably will be okay. So Mars probably will be, I don't know, 3, 5 AU away from a white dwarf, like in 5 billion years. That's probably still be fine. So I think that's the first thing. In a later part of the talk, I will tell you about some planets we've discovered or we're working on around white dwarfs. And then the second question is, should these debris be blown away by the stellar wind? Yes, so kind of whatever, I guess, zodiacal light and stuff existing in the solar system, I think they would have been blown away during the red giant stage and things. But the specific debris we are talking about, these are the debris kind of formed after the star become a white dwarf. And then I won't go into much detail in this talk, but these kind of debris, we call debris disk around the white dwarfs, they are quite different from the common debris disk or protoplanetary disk. They are like very, very hot. They are about 1,000 Kelvin, like black body temperature. And then they are actually within the tidal radius of the white dwarf. So we think most of them are within the tidal radius. So they are super small and super hot. And they are formed by kind of this tidal disruption process. And they don't last very long. They last, I don't know, maybe about 1 million years, the time scale. So those kind of dust, they are rarer. Maybe 3% of white dwarfs have this kind of dust. So yeah, hope that answers your question. Yeah, yeah, thank you. I think we have a question from Sasha. Yeah.
Yes, hello. I was wondering, like, what is the sort of settling time? How active does it have to be accreting for you to get a signal?
Yeah. Okay, that's also really good. So that's also a really good question. Just making sure you're asking about the settling time in the white dwarf's atmosphere.
Yes. Yeah.
Okay. Yes. So yes, so because the white dwarf has very high gravity, right? So material do settle out of the atmosphere. The settling time actually kind of dependent on the property of the white dwarf, and the temperature and whether it's hydrogen or helium dominated white dwarf. Anyway, it's very, very short in the sense for the hotter white dwarfs, it could just be days. And then for the cooler ones, it's a little bit longer, maybe 1,000 or 10,000 years. But in general, like the settling time is still much shorter than, say, the cooling age of the white dwarf, which is like gig years. That's why, like, I don't know, maybe even 20 years ago, we don't really expect the white dwarf to show kind of any of these kind of material. So white dwarfs are kind of used as a clean slate. You can use it to study interstellar media, like, and all these things. Yeah. Anyway, for the purpose of this, just in general, the settling time is ranging from days to like maybe at most 1 million years. Yeah.
Thank you.
Thank you. Good questions. Anything else before I move on? Okay, now I've convinced you polluted white dwarf as a method, and I want to share with you the other method that we have been developing along the same theme. Is for maybe the past few years, we have found a lot more white dwarfs. So I guess previously I've been talking about the polluted white dwarf, right? The atmospheric model and all the things. It works great, but every model has its limitations. So recently we have been working on trying to use modeling the circumstellar gas, because if this cartoon is correct, basically both the dust and the gas are all coming from this disrupted asteroid. And then the material would be coming to the white dwarf, right? So if we can catch them before they fall onto the white dwarf, that would be really neat too. And then we can kind of also back out the composition of the gas. So this is really only possible because, let's say, because of we have discovered a lot more white dwarfs with circumstellar gas. Now we have about 30, and a lot of them show like various emission lines. Before we only see calcium, so you can't do much with one element. Now we've seen like systems with quite a few different circumstellar gas emission lines. So that's just make it more interesting. So yeah, so here I'm just trying to show the blue line is photospheric, so white dwarf atmospheric element detected, right? And then the red one is actually the element have been detected in circumstellar gas. So it's becoming respectable. So I was like, okay, so let's try it out here. Then I'll tell you, this is ongoing work. This is a pilot study. We focused on one white dwarfs. So yeah, this is the white dwarf name. And then anyway, so here I'm kind of showing you the most complete spectra of this white dwarf we have. So it's going from NUV from the Hubble Space Telescope to like optical, which we use the VLT and X shooter. So this is kind of like a blue to like red, right? And then all the way into the infrared, we use Gemini flamingos too. Then I'm kind of highlighting, we'll see a little bit later too, I'm kind of highlighting all the emission lines we have seen. So the strongest is this calcium infrared triplet around 8,500 angstrom. And then previously, most of the gas emission line system only show this line, which you really can't do much. But in this specific case, we actually find like, oh, at least five, right? So it's calcium, magnesium, oxygen, silicon, sodium. I'm like, okay, maybe we can do something with it. So marking the lines that we are trying to model, just taking it a little bit a step further. Now I'm plotting the lines in kind of velocity space. Again, so this is the velocity, this is flux, and I kind of offsetted them a little bit. So that just give you a sense about the line. So I just want to point out, first that the line is very symmetric. Again, it's good. I think it indicates the gas is in a circular orbit around the white dwarf. There are a few other systems that we also see such lines, but they are much more asymmetric. And they also appear to be changing. So again, make modeling very hard. So like we want to start with a nice and easy one. So we do this system. And also I just want to say, look, the width of the line goes from about, minus an 800 kilometer per second to plus 800 kilometer per second. So it's actually very, very wide. So based on the width of the line, you can kind of back out to the location, right? If you assume they are in circular motion, they are being capillary and broadened, that kind of gives you the geometry of the disk. I won't go into too much details, but basically we use the photo ionization called cloudy. We kind of assume the white dwarf is the only ionization source, and then there's like kind of gas around it, there's a gas cloud around it. So our goal is basically trying to see if we can reproduce both the line profile and the line strengths. And then with that, we can try to back out the composition of the circumstellar gas. So that's kind of the idea. Yeah, and I will show you some model fit. I'm not a modeler, but this is kind of my first modeling project, which is kind of fun and different. So here, again, the x-axis is the velocity, and the y-axis is a flux unit. I was trying my best to work in absolute flux unit. So the black line is our data, and then the orange line is the model. And then the solid orange line is the final model, and then the dashed line is if there's two components. Because for example, if you see here, the sodium line is actually a doublet, right? So you need a 1, 2, I need to add them up together. And then the same, the oxygen one is also actually a doublet. And then this is calcium, and this is silicon. I saw to my observer's eye, it looks pretty good. It looks close enough. All right, so once you have all that, we can back out the gas composition. And this is actually also a very heavily polluted white dwarfs. So we have a postdoc, Laura Rogers. We have been working on getting out the composition of the white dwarf photosphere. Then we can kind of make this plot, right? Basically, we are comparing the gas composition with the photospheric composition. So I'll walk you through the details. So here we are plotting the number of an element relative to silicon. And then, yeah, so this is basically oxygen over silicon, sodium over silicon, magnesium over silicon, calcium over silicon. And then I'm showing the both for the gas, the photosphere, and the Earth. So for me, I feel like this is interesting because we actually do not have a photospheric sodium measurement. So we can give an kind of an additional constraint. For this method, the error bar is still kind of big, and then details, but throughout the process, we find that some gas lines are actually optically thick, which means we can't quite constrain the amount. We can only put an upper limit. That's why you can see like this upward arrow. Lower limit? We can only put a lower limit. That's why you can see an upward arrow. But still, I guess our best constraint in this case is really oxygen and calcium. So I think it's actually the agreement is pretty good. Like we didn't really find any significant difference between the photospheric value and the circumstellar value, which is kind of good. You might say, okay, oxygen, it may be a little bit elevated, but it's really all consistent within the uncertainties. So what we really would like to do is to develop this method more to better understand the circumstellar gas composition, because I think that would be really neat if we can, I mean, if they agree, that's also very good. Like, but if we can see a difference between the circumstellar gas composition versus the photospheric composition, maybe it tell us something actually about the internal structure of the object, right? Maybe it is differentiated and we are seeing core and mantle different part, like falling into the white dwarf differently. Or maybe if there's a difference in the volatile content. So maybe volatile material get, I think it's actually called an asynchronous accretion. Amy worked a lot on that. So it's kind of different material would get onto the white dwarf at different time. And then this will be an observational signature we're looking for. Okay, with that, I think that's a summary of this part of the talk. So we are working on a model to understand the circumstellar gas composition. I think it looks quite promising, and we have still a few things to sort out, but I think it looks pretty promising. And then just overall for this composition analysis part, I think we really would like to know what is the property of the population, right? Can we draw anything conclusive in terms of, say, like the mass of the star, or like even the age of the star, age of the star, yeah, or like, can we kind of say anything like overall property of these systems? And also, more like take a step back. I think it's very important to understand the systematics, both in terms of the systematics analysis for the polluted white dwarf work, and the systematics, say, using like the cloudy model to do the gas composition. Okay, so I'm going to make a pause and take questions. I see the one from the chat. Yeah. Yes. So the question is, I think it's back to, is there an upper limit on the photospheric sodium? So here. So yes. It's hard because this is the strongest photospheric line, and you see it's also the circumstellar gas emission line. So like so I suppose you can, yeah. So basically it's very hard. Yeah. Yeah, I know. It will, but like, yeah. Okay, I'm gonna leave it here and see if there are any other questions. Okay, I guess if you are the referee, you will like the paper. Anyway, it's on the refereeing process.
Do you want to continue with the talk, and then we can have more questions at the end of the discussion?
Okay. Yeah. All right. Sounds good. Yeah. Okay. I'll just continue on. Yeah. Right. So I'll talk about So are there really planets around white dwarfs? I guess I ask this question. So yes, actually, yeah, we have found quite a few planets around white dwarfs. I'm very proud I can actually make this kind of figure now. Because when I first started on my PhD, I feel like the zero. So like whenever I talk about polluted white dwarf, people would ask me, have you found a planet yet? Right. So anyway, so here I'm plotting planet mass and also orbital separations. And then it really, to me, it's really amazing that we have 4 dots up there, and then each of them are using very, very different methods. And kind of in terms of timeline, this is the first object detected using Spitzer. So it's a very wide binary. So it's like common proper motion pair, right? And then you can see it's like thousands AU away from the white dwarf. I think it's about 7 Jupiter mass. So at the time, it's the coolest brown dwarf, right? So I think this one, they probably formed, if it already formed together with the white dwarf, they probably formed more like 2 separate stars rather than like form like a planet. or like this could be captured later, like was captured at a later process. Anyway, so there was one discovery kind of more than 10 years ago, like a planetary mass object around a white dwarf. And then there was quite a few development more recently. There's this guy, which this is a evaporating Neptune. So, and in a sense, the planet is kind of slowly going away, right? So basically what they find is they find a very volatile rich disk around the white dwarf, which is very contrary to what I talked about earlier. They are all rocky. Basically, they didn't see any calcium, silicon, iron line. They only see sulfur and oxygen. So I think after going through all the other possibilities, they think the best explanation is we are seeing kind of an evaporating hot Neptune kind of around this white dwarf. So that was in 2019. And then there's this object, which is detected by microlensing. So it's about a little bit over like 1.5 Jupiter mass object, like about 3 AU away from the white dwarf. So to me, this is the most normal system because that's kind of fits into my cartoon understanding about where we expect the planet to be, right? About a few AU from the white dwarf, like this kind of object. But the harder thing there is by microlensing. And if you read the paper, the reason they back it out to be a white dwarf is because they tried very hard and they could not detect the system. They used the CAC-AO. They put an upper limit to be like 21 magnitude. And then they say because they could not detect the star, it must be a white dwarf. So they use that to back out. Okay, so there's like 1.5 Jupiter mass planet around this white dwarf. So it's good to know there's such population out there, but it's hard to do kind of follow-up studies. I think this is very good for statistics, which is kind of the microlensing study is. Then I want to tell you a bit more about this, which is transiting planet. We still call it a planet candidate because we can't quite pin down the mass of this object. So the mass actually can go anywhere between 1 to 12 Jupiter mass. So 1 to 13 Jupiter mass. So technically it could be a brown dwarf. Maybe I'll tell you a bit more about this system, which I'm actually quite excited about. So this was first discovered from TESS. Which is a transiting exoplanet survey satellite. So here I'm just showing the light curve in different band. You can see from TESS, from ground-based, and all the way to Spitzer. So the good thing there, it's very stable, it's symmetric, and it's periodic, and it's not changing, which is very nice. And then we find that the transit depth is actually very deep, so it's 56%. The reason is just because the white dwarf is tiny, right? So in comparison, the transit becomes really deep. Actually, when you back out the radii, the planet is bigger than the star. The duration is only 8 minutes, very, very short. The period is 1.4 days. So again, like to me, I don't really expect such a big object so close to the white dwarf. And it's a Jupiter-sized object. And then we find that the semi-major axis is actually only 0.02 AU. And then if we work out the equilibrium temperature is 163 Kelvin, which is only a little bit hotter than our own Jupiter. Okay, so there's a question. Yeah, maybe I'll just, yeah. What mechanism bring the planet material inward if it starts out beyond the 1 AU, not to be inside the giant? Yes, exactly. So that's a very, very good question. And so it basically asks, what is the mechanism bring the planet, or even say this planet, close to the white dwarf, right? I don't think it could be there. So I think there has been a lot of literatures and studies kind of different. I think a lot of them are just different dynamical interactions, maybe broadly different dynamical interactions, planet scattering, cosi, or like sometimes there will be some kind of secular evolution, say like galactic tides and the things. So in this specific system, I think a cosi might work. Maybe I will first lean on here because that's a really good question about what mechanism. I think we can talk about it for a very long time. So I'm gonna hold that and maybe we'll finish this system and then we can go back to that at the end. Yeah. Okay, so at the time when we discovered it's a Jupiter-sized object, we're just like, okay, we really want to pin down the mass, right? Because Jupiter-sized object can be an M dwarf, a brown dwarf, or an exoplanet. How do we do that? So we first tried to characterize the white dwarf. So we took the spectrum from like optical, like all the way to infrared with Gemini. And it turned out it's a DC white dwarf, which means there are no spectral lights, right? Because usually in exoplanet study, when you find this, you follow up with radial velocity, you pin down the mass, you're down. But this white dwarf do not have any spectral lines, of course, right? So you can't really do that with the mass. So anyway, so it's a pretty faint host star. It's almost 17th magnitude. It's a DC, which means there are no spectral lines. The temperature is about 5,000 Kelvin. It's actually a little bit cooler than our sun, even though it's a white dwarf. Anyway, it's a 0.5 solar mass, and it's actually in a triple star system. So I think that makes the dynamic really interesting. So I want to say, so see, this is a white dwarf, and it's actually have an M dwarf pair, which is co-moving with the white dwarf. So that's really interesting. But anyway, so we still want to know the mass, right? So how do we figure out the mass of the system? So what we decided to do is actually by measuring the flux. So we got a Spitzer light curve of the same system, right? So our idea is if the companion is hot enough to emit some thermal emission in the infrared, so this is Spitzer at 4.5 micron, then we may be able to detect this light from the companion, and then we can use that to back out the mass. That's kind of the best we can do at the time. And then if you see this light curve, you find the depth is basically the same, which means even at 4.5 micron, we did not detect any light from the companion. And then with that, and coupled with some like brown dwarf giant planet models, given the total age of the system, which is about like 9 to 10 gig years, we can back out the mass to be lower than 13.8 Jupiter mass. That's why, I mean, technically it's still a planet candidate because it can just be maybe a brown dwarf. So we do get JWST time. Actually, we got data trying to kind of repeat this experiment and see if we can detect the thermal emission from this object. So that would really help us understand kind of the mass evolutionary history of this object. Yeah. And then for me, since I'm quite intrigued by this object, like this is probably the coolest transiting exoplanet known, like and it have gone through so much, right? Can we learn anything more about its atmosphere? That would be really interesting too. So we tried to get a transmission spectrum of this object with Gemini GMOS. And just want to say it's a very challenging object because you see the transit is only 8 minutes, right? And then the duration is very short. So we have to get, for people who are used to doing transit, it probably lasts like hours, like 5 hours. But here it's just 8 minutes. So we have to get 10 transits in total in order to build up enough signal to understand what's happening. So just this is the kind of the individual light curve. First, I was very proud. I did the calculation correct. So we did catch the transit every time, right? Like, but you can see each transit, we really only have like 6 data points because it's 8 minutes, right? So yeah, so this is quite a fun data set to work with. Anyway, I learned a lot. And then we kind of put them together. So this is like the white light curve, and we kind of try to break them down into different bins and stuff. And I just want to highlight another difference. As we were doing this analysis, we're like, wait a second. So what are we really looking at? So for normal exoplanet transit, from this transit light curve, you can extract the ratio between the planet and the star, right? And then the transit depth is basically that square. But in this case, the planet is larger than the star, and it also it's like a grazing transit, right? So how do you do that? Work with some very brilliant theorists who basically first let's just check out the video, okay? So this is the planet, this is the white dwarf, right? This is kind of a model transmission spectra. Now you can see it really changes, and it actually changes in 2 ways. Oh, okay. I want to play this again. First is you can see like the overall depth of the transit changes, right? And then the second is because we are really only seeing this thin, small layer of the atmosphere. And then so depending on when you see it, the feature also changes, right? So yeah, so we have to come up with a little bit mouthful, but I think that really captures what it is. We have to use something called lane darkening corrected time average transit depth. Because I think that's the best way to capture like the transit signal we are looking at. Okay, so after all this, we have to develop this whole technique to be like that's what we are analyzing. Yeah, so this is kind of the final spectrum. We consider 2 models. One is clear, one is cloudy. And then the green line is our final transmission spectra. I know it's a little bit disappointing for me because it's just a flat, straight line, right? the hardest I will ever work to prove is a straight line. But then my friend told me it's not too surprising. Most of the exoplanet kind of look like that. So anyway, so we don't think we're seeing any significant features in this optical transmission spectrum. But we also got JWST data to go into the infrared, because as you can see, methane, like there's a lot of stronger features in the infrared, and this target is very well suited for that. So we are happily analyzing the data to see like what's happening there. Okay, with that, I think that brings me to second part, the summary of this part. Hopefully I've convinced you we have used very different methods to detect planets around white dwarfs, and a lot of them is quite surprising to me, actually. And then I think really the open question is really what is the population of planets around white dwarfs, and how do they get there? So maybe, I feel like I've talked a lot. Maybe I'll just make a pause here to see if there's any questions. Or Amy, do you think I should just stop here maybe? Because,
yeah, I think that would be a good place to stop. Thank you, Siyi. It was a really exciting talk. Has anyone got any questions that they would like to put to Siyi? If not, go on. Claire's got another question. Go, Claire.
I might have a question.
Sorry, is this like questions about the whole thing?
Yeah.
No? Okay. Yeah. I have a question that's kind of similar to what I asked earlier about kind of identifying differentiated planets and comparing it to chondritic compositions from the solar system. But okay, so what I understand just from looking at main sequence stars is that the fracture elements vary a lot, and different star systems will have different, chondritic compositions. And how is there like any way in establishing what the chondritic composition of these systems are, or is that something that we might be able to do? Does that make sense as a question?
Yeah. So okay, maybe my first question, just want to clarify. You are saying by looking at the main sequence stars, you find the like refractory elements vary by quite a lot.
Yes.
Right.
Yes.
Okay. Yeah, but yes, but maybe I think one limitation, or maybe I would say, is your idea of varying a lot to us look like the same. So
okay,
right. I think for the white dwarf abundance analysis, I really think the state of art is probably between 0.1 to 0.2 dec. Is a typical uncertainty, right? And I think 0.1 to 0.2 dec might already, like, I know for main sequence you probably can do a lot better, right?
Yeah, exactly. Yeah, I'm talking about like change by a factor of 2. Yeah. And I agree, something like calcium,
yeah, exactly.
You're not going to have a crazy amount of calcium compared to silicon or something. But I'm just kind of generally interested in, is there some way of telling what the kind of like bulk composition or of planetary building blocks looks like from these measurements?
Yeah, Amy, do you have a thought? Yeah.
I can answer that if you want, Claire.
Sure, yeah.
I think it's really, really hard to know which kind of star. So you can think about the age, and you can think about what happened in galactic chemical evolution to make a prediction. Or what we're doing is trying to use stars in wide binaries where we can see the binary companion to know probably what the composition of the whole system was.
Mm-hmm. Great.
Yeah, exactly, I agree. I think that's a I was gonna say that's a technique. I feel right now for polluted white dwarfs, I feel like you can. I'm confident to make order of magnitude statements. Like, so I guess we are not seeing something like 90% of silicon, but I don't know like how much detail we can. So that's why I guess for me, I'm trying to see, okay, are there, maybe we can say something from the gas, maybe we can see something from, I talk about like the dust mineralogy by using JWST. Maybe these are the things can give us additional constraint on that. Or somebody needs to work very hard on the modeling.
Yeah. Oh, okay, thanks.
Super. There's another question from Matt.
Thank you.
Martin,
there's another question from?
Hi there.
Okay.
Hi there. Let's see.
Hi.
I'm trying to, that's better. So thank you for your talk, very interesting. So when you were talking about the star going behind the planet, but only partially, obviously the first thing that comes to mind is we should see stuff from the atmosphere of the planet appearing in the spectrum of the star. Did you see that? Or?
Just making sure you're talking about the primary eclipse or the secondary eclipse, right? That's what you're kind of.
Sorry,
Is that what you're talking about? Sorry, I
No.
just want to make sure. Are you asking about the secondary eclipse?
The what? Sorry.
The secondary eclipse. Are you talking about when the planet goes behind the star? Do we see anything there? Is that your question?
Planet goes. So you were showing the animation. It had the star going behind the planet, but only partially. Right? That's what you showed the last time.
Right.
So the starlight comes through the atmosphere of the planet there. Right?
Right. So yes.
Do you see the atmosphere of the planet appear in the stars, in the stellar spectrum?
Okay, maybe I will just share my screen again. See. So you're just talking about this slide, right? Yeah.
Right. So the star is the white star there. So yeah, I would expect that at that point now you would see, stellar light going through the upper layers of the atmosphere of the planet. Like a partial, like a radial occultation in a way, except you're doing it with light. So
yes,
I was wondering whether you could see the parts of the atmosphere of the planet there appear in the spectrum of the star.
Yeah, actually, I'm glad to see Ryan here. Ryan, the person who made this animation. So Ryan, would you like to give a comment on that? Good to see you. Good to call you out.
Yeah, transmission spectra are a differential measurement, so where you kind of like cancel out what the star is actually doing. But in the right panel of that animation, the actual blue lines that you were seeing there were exactly features from the atmosphere of the planet that were imprinted in there. So
right.
you'll see that when you're at the center of the animation,
right,
when most of the surface area is occulted, then you see all the lines are intrinsically stronger because more of the star is being occulted at that time.
Right. So
the absorption lines get stronger depending on the fractional area occulted.
Okay. I was wondering whether you could learn something about the atmosphere of the planet there. I know that's not the topic of the talk, but
yes.
I think in a way we are trying to do that, right? We are trying to trying to learn kind of what we can see in the atmosphere of the planet. I guess in the optical, in this specific case, like the features are too small and we didn't really see it. But Ryan is working on the JWT spectrum, which I think will be really cool. Anyway, thank you for helping me out.
All right, thanks.
Yeah, thank you.
Thank you.
Ryan, I think you had a question as well. Do you want to go next?
Yes, I did, and thank you for the fantastic talk. I was just wondering about what your thoughts were about the prospects of finding intact rocky planets around white dwarfs, which would be spectacular for atmospheric character.
I know, exactly. I think we're all working, right? Just to me, it's just amazing. Like the 4 dots there, it's 4 different methods. So I think transit, like more transit would definitely be like through the transit technique. I think because tests is still ongoing, but I mean, Andrew Vandenberg has been working very hard, right? We haven't found any, which I don't know. So, right, test is still ongoing. And then maybe with Ruben, with the LSST, maybe we'll like, it goes so much deeper. I think maybe we can find a lot more. So, I think in terms of atmospheric characterization, that's probably like really the best way. But otherwise, like Gaia, maybe with an astrometry planet. For a while, we were all excited about that possible like astrometry planet candidate, right? So things coming along, but I do think there's a lot of data coming. We just need to be on top of that. Or even ZTF. ZTF is so successful. I didn't really talk about this today, but ZTF is so successful in finding those disintegrating asteroid, right? And then like I think we can learn a lot from the disintegrating asteroid too, because in a way, like we get I mean, in a way, it's very similar to what we're doing here, but we can constrain kind of the dust property, and maybe we can even constraining like the actual composition of the material just by like the light curves. So I think that may be like another way just to constrain like the rocky composition. Yeah, hope that helps. Thank you.
Thank you. I think there's another question from Martin, if no one else has got any questions as well.
I guess there's a
Go
question
for it.
from the chat, but maybe Martin can go first.
Oh yeah, do the one in the chat first. So maybe.
Yeah.
Oh, okay,
What
sure.
are your thoughts about how this data could be used to determine the potential habitability of planetesimals orbiting white dwarfs, regarding all the elements, but most specifically oxygen?
Ooh, okay, that's another really good question. Like, how can we tie this specifically to the habitability? I feel like there's so many angles you can tackle this question. I think people have focused a lot on oxygen. I guess in this case would be water, right? So we're really trying to assess like how many of these polluted white dwarfs are likely to have water, and then if so, maybe that give us an argument. Okay, if a lot of them, I think if most of them have water, then maybe like that's really good news for life. So I think that's one angle. And another angle I kind of like a lot is my PhD advisor had this idea about looking for baryon because it's a sign of plate tectonics. You know, because on Earth, like on Earth's continental crust, the baryon fraction is like 2 orders of magnitude higher than anywhere else, like than any other material. So, and we tried that. Baryon have not been detected in polluted white dwarfs yet, by the way. But like, if a polluted white dwarf had accreted any kind of material representing continental crust, and if it had plate tectonics, many ifs, so the baryon abundance would be very increased, and we actually can detect them. So I feel like a lot of I feel like a lot of elements have an interesting history. Like if we look deep into that, maybe can really tell us about like the habitability of that object. Hope that helps.
Yeah, really fun answer. Martin, do you want to have a very quick last question?
Quick last one. So what's the time scale of the disruption when you get the planet close to the star and then it starts being shredded apart? What's the time scale, and do we have any chance of observing, you know, of capturing that moment, or that time moment would be really great.
So I saw the timescale is very, very short, but you know, we have observed about 24 of them in the process of disintegrating. I guess that's what I was talking about. So the first one is WD1145. It's discovered by K2. Basically, so what we are seeing is basically very asymmetric light curve, kind of like a disintegrating planet around main sequence stars, but they are much more extreme. Like now, like mostly with ZTF, there's about 24 such systems, and the light curve is just crazy. Like some of them do not even have periodicity, and some of the transits last for years. You know, it will last for a year, and it has so much structure. So that's why I feel like it's really a very rich field. And then a lot of them have polluted atmosphere, have a dust disk. Everything seems to be coming together. I was really surprised. I thought we would not be able to find such a system happening because in my mind, tidal disruption, I don't know, maybe 1,000 years, 10,000 years. But the fact we find quite a few makes me think like maybe they're not that rare, and it's actually happening. Yeah.
Brilliant. Thank you for that last question and answer. And let's thank Siyi again for a great talk. It's really, really enjoyable. Our next talk will be on the 7th of December, and Emmeline Beaumont is going to be